Okay, now let's see next question. A ball has been tossed up. Which is the correct free body diagram just after the ball has left the hand? And let's ignore the air resistance. I will give you some time to think about it. Please pause the video until you get your answer. Okay. I guess now all of you have got your answer. So, after the ball left the hand, how many forces are exerted on the ball? So we have talked about this situation many times. Once the ball left our hand, what's the motion? We have a name for this special motion. It's called free fall motion. So in free fall motion, there's only one force, which is the weight. So the correct answer is D. There's no any other forces exerted on the ball once it's left the hand. Okay, now let's see this question. A ball hanging from the ceiling by a string is pulled back and released, which is the correct free body diagram just after its release. I'll give you some time to think about it. Please pause the video until you get your answer. Okay, so I think now you all have your answer. So first of all, let's see what is the answer. The answer is B. Did you make it correct? Okay, so let's see the ball. First, as we talked before, there's always one force on your object, which is weight. Is there any other forces on the ball? Actually, there's a tension force, which is in this direction. Is there any other forces? No, there isn't any other forces. So the correct answer is B. Here, that's another example. A car is parked on the hill, which is the correct free body diagram. So I will give you some time. Please pause the video until you find the answer. Okay, I guess now you have find your answer. So now let's do it together. So how many forces are here on the car? The first force is always the weight. Is there any other forces? Yes, there is a normal force, which is perpendicular to the direction of the ramp. Let's say it's perpendicular, 90 degrees here. Normal force. Is there any other forces? Okay, so the car is stopped here. That means there's some friction. Because imagine that if there's no friction, what happened? What will happen to the car is the car will go down if there's no friction. So actually the friction play a role to stop the car. Okay, so that is all the forces. Did you make it correct? Another question. A car is towed to the right at constant speed. Which is the correct free body diagram? Okay, this time let's do it together directly. The first force is always weight. The second one, of course, it's normal force. And the third one, of course, it's the tension force because the car is being towed. And does the car has any friction? Now, let's see, the key word is constant speed. So the car is towed by constant speed, means the acceleration is 0. If the acceleration is 0, then we know the net force is 0. This is Newton's second law. Do you remember that? If there's no net force, then there's no acceleration. If there's no acceleration, there's no net force. So the net force should be 0, means the weight and the normal force should balance each other, and the tension force should balance another force, which is friction. So the answer is D. Okay, now let's see an example here. An elevator suspended by a cable speeds up as it moves upward from the ground floor. Draw a free body diagram of the elevator. Okay, so first we know there are two forces. One is weight, the other one is tension. The most difficult part is which force is greater, because there are two keywords: speeds up and upward. It's moving upward means velocity is going up, and its speed up means the acceleration is in the same direction of velocity. If the acceleration is going up, that means the net force is going up. If the net force is going up, okay, actually we derived it from the velocity to acceleration to net force. If the net force is going up, then the tension force should be greater than the weight. Okay, this is the way to solve this problem. Okay, another problem. A tow rope pulls a skier up a snow-covered hill at a constant speed. Draw a full version overview of the skier. Okay, that's another free body diagram question. There are several keywords like up, so the skier is going up, and then constant speed. That's very important. If there's something in a constant speed, that means acceleration is 0. So acceleration is 0 means net force is 0. Okay, now let's see how many forces are exerted on the skier. So the number one force is always weight. That's the number one force. It's being towed. So tension, and there should be some normal force from the ramp here, and there might be some frictions when it's going up. When the skier is towed up, then there might be some friction going down. So that's all the forces shown here. Okay, another problem. So this problem should be a good practice for you. Please solve the problem by yourself. Okay, so last section, Newton's third law. We have introduced the Newton's first law and second law. Do you remember what are the first law and second law? If you don't remember it, please please go back to check your note or check your slides and see what are the Newton's laws. So Newton's first law tells us if there's no force on one object, or if the net force on one object is zero, then this object should be keep moving in uniform motion, or it should be at rest, because at rest is a special version of uniform motion, which is uniform motion of velocity equals to zero. That's Newton's first law. Do you remember what is Newton's second law? Newton's second law is simply describing the relationship between net force and acceleration. Here, this is Newton's second law. It tells us if there's acceleration, there should be a net force on an object, and they are in a proportional relationship, and they're in the same direction because there are two vectors. So that's Newton's second law. Now let's see the third law from Newton, which is Newton's third law. Motion often involves two or more objects interacting with each other. As the hammer hits the nail pushes back on the hammer. So this is a very common phenomenon. When the hammer hits the nail or pushes the nail, then the nail is pushing back to the hammer. This is very common in any other type of forces. For example, if you push a table forward, actually the table will push you, will exert another force on you, which is pushing you back. So if you want to push the table forward, then the table will push you backward, like the hammer and nail. Another example is a bat and a ball, or a foot and a soccer ball, and the Earth and Moon system are some other examples of interacting objects. Let's talk about them one by one. A bat and a ball. So if there's a bat hitting the ball, then the bat will give the ball a pushing force, which is pushing forward, and the ball will give the another force on the bat, which is pushing the bat backward. The same thing to foot and soccer. If the foot, let's say, is kicking a soccer ball like this, then the foot will give a forward force to the football, and the football will give a backward force on the foot. And also the Earth and Moon. So the Earth is attracting the Moon, and the Moon is attracting back the force. So this is called interacting objects, or interacting pairs of objects. So when there is a force, there's always some interacting pairs. So here, an interaction is a mutual influence of two objects on each other. The pair of forces shown in the figure is called an action-reaction pair. An action-reaction pair of forces exists as a pair or not at all. This is Newton's third law. Newton's third law has several statements. So first of all, it says an interaction or force between objects is always a mutual influence between two objects. This is the first statement. The second statement, there's always a pair of force shown. Actually, there's always a pair of force, which is called action and reaction pair. If you find one force, you will be able to find another reaction pair of the force. And an action-reaction pair of force exists as a pair. So you cannot find a single force which doesn't have its reaction force. So for example, if the box B is pushing A, then A must pushing B back. And another example is if the hammer is hitting the nail forward, then the nail must hit the hammer backward. So now let's see Newton's third law. Every force occurs as one member of action-reaction pair of forces. The two members of action-reaction pair act on two different objects. The two members of action-reaction pair points in opposite direction and equal in magnitude. For example, for the hammer hitting the nail, when the hammer is hitting the nail slightly, then the nail will hit back on the hammer slightly. If the hammer is hitting the nail heavily, then the nail will hit back on the hammer heavily. So, because they're equal in magnitude, this pair of force is called action and reaction. And the pair of action and reaction forces that act on two different objects. One is on hammer, the other one is on nail. This is Newton's third law. And here are some examples on Newton's third law. For example, in order to move you forward when you are walking, the floor needs to have friction so that your foot sticks to the floor. As you straighten your leg, move the body forward. Actually, when you're moving forward, the surface of the road is pushing you forward, and your feet is pushing the road or the surface of the road backward. Does that make sense? Think about when you're running fast on let's say a rocky or sandy road. You may figure out sometimes you will see some little rocks or some sand pushed back while you're walking or running. That means you are pushing the surface of the road back so that the surface of the road is pushing you forward. This is action and the reaction pair. And another example is when the car is running on the road, the tire of the car is trying to push the road back. Meanwhile, the surface of the road is pushing the tire forward so that your car is moving forward. That's another pair of action and reaction. Here is another example. When a rocket is launched, let's say when the rocket is moving up, the rocket will push some air downward. When the rocket is pushing air downward, the air is pushing back to the rocket, which is pushing the rocket upward. This is another pair of action and reaction. Okay, so after the explanation of action and reaction pair, which is the Newton's third law, let's see several examples. So first of all, 10-year-old Sarah stands on the skateboard. Her older brother, Jack, starts pushing her backward and she starts speeding up. The force of Jack on Sarah is... which one is correct? I'll give you some time to think about it. Please pause until you find your answer. Okay, the answer is B. So the force Sarah pushing Jack is the same magnitude of the force for Jack pushing Sarah. because they are action and reaction pair. Due to the Newton's third law, the magnitude of those two forces are the same. Now let's see this example. It's a little bit tricky and a little bit confusing, but please try and try to see which is your answer. Please read the question and find your answer. Please pause the video until you find the answer. I will give you some time. Okay, I guess you have made your choice. So when mosquito hit the truck, so which force is greater? So the truck give a force on the mosquito, and the mosquito also give back a force on the truck. Which force is greater? The answer is they are the same. So it's not very intuitive because when mosquito hits the truck, it's easy to understand that the truck maybe give a big force on mosquito because the mosquito dies, right? But the truck seems like nothing happened to the truck. However, the forces from the truck to mosquito and the force from the mosquito to the truck, they are the same in magnitude. The only difference is they are in different direction. Actually, they are in opposite direction because this is a pair of action and reaction. Simply because the truck is heavy and the truck is strong. The mosquito is light in weight and the mosquito is too soft. So the mosquito is easy to be destroyed and the truck seems like fine. There's nothing happens to the truck. But the forces on the mosquito and the truck are actually the same. But don't forget that even a small force can destroy or can kill a mosquito. So the mosquito dies, but the truck is fine. Okay, so that's everything about the chapter 4. So here's a summary of the entire chapter. In the entire chapter 4, we have learned 3 Newton's laws. The first law, which tells us if the net force is 0, then an object should be in a uniform motion, or it should be at rest. And then we learned Newton's second law. The Newton's second law tells us the net force is in the same direction as the acceleration and they're in proportional relationship. Sometimes we write the equation in another format, which is net force equals to ma. Okay. And then Newton's third law. In Newton's third law, we learned that if A is pushing B, then B must push A back. This is action and reaction pair. So any force is in the action and the reaction pair. If there's one force from A to B, then there must be a reaction from B to A. They're in the same magnitude, but in opposite direction. So this is Newton's third law. Okay, so that's everything in this chapter. If you have any questions, please leave a comment to my video, or if you don't want your question to be public, you can maybe send me an email or something. Then I'll answer your question. Thank you.